This is Investigation 4, Lessons 1 and 2. We're going to start off with the entry ticket together. It says a lacrosse player sold raffle tickets for their annual fundraiser for 6 weeks. The table of values is a record of how many tickets were sold each week. So on the left side of the graph, we have the number of tickets. That's on the y-axis. And then on the x-axis, we have weeks. So I made a little scatter plot. You can do this in Desmos. So I'm going to show you how to do that in Desmos real quick. Here in Desmos, if you just hit this plus sign and hit table, you're going to be given a table, and you can just plug in your values that way. So what I did was I already actually had that done for you on the side over here. So if you see these green dots, this is your scatter plot. Now, they ask us to create a linear regression model for this data, and it says to write the equation below. So when we're dealing with regression, we're dealing with a line of best fit. So if we are asked for a linear regression, we need something in the form of, okay, well, y is approximately mx plus b. That's the equation we're used to solving whenever we have a straight line, right? It's always in y is equal to mx plus b form. So what we're going to do, and the same thing for quadratic, actually, in cubic, right? So for quadratic regression, we know we're going to have x squared as a leading term. For cubic regression, we know we're going to have x to the third as the leading term. And that's what we have. These a, b, and c, and d values are placement variables for leading coefficients. So it's basically telling you this is the equation of your graph, and there's a variable in place for every single value that graph would have, right? So whenever you're doing a line of best fit, you could do linear, quadratic, cubic, and we're looking for a straight line that's the line of best fit. It could be a parabola that's the line of best fit, or it could be a third degree polynomial. So looking at this line, you can kind of already get an idea that the best line of fit would probably be a straight line. I don't think it'd be a parabola, or else you'd have points down here and down here. And if you had a third degree, it would look like this. So we don't really see anything along those lines either. So we're going to do one of each. So if you go to Desmos, that is where we're going to do all of our linear regressions. So here, so you'd hit y, and I have y1, 2, and 3 already. So, but in your case, you'd put y down 1. So y1, the first line, would have approximately, we're going to put this approximate symbol, ax1 plus b. So this would be an approximate equation for a line of best fit that was linear, right? So straight line, which is why there's only a degree 1. I put this sub 1 because that's just telling you there's only one x in this entire equation, right? So that's how you'd fill it in, and then here it will give you your values for a and b, and it will tell you what your equation could be. You can make it, right? But I'm going to erase this because I have it up here, and I did the same thing here for a quadratic regression. You know you're going to have a parabola, so it's going to be a degree 2 polynomial. And here I have x sub 1 and x sub 2 because in this equation, we have two possible terms that have that x value on them, right? You have one that's to the first degree and one that's to the second degree. Similarly, for the cubic regression, you'd have ax sub 1 to the third power, right? So that's your first x. It's always to the third power. Then you have an x to the second power, and then you have an x to the first power. And we have three x's, so x sub 1, x sub 2, and x sub 3. That's telling you that it's the same variable, but there's three terms that have that variable attached to it, right? It just happens to be in different degrees. So here I have put in my linear, my quadratic, and cubic regressions. I'm going to try to find a line of best fit that's linear. If I click that blue, this just shows up when I click it. You can see that there's a linear regression that almost perfectly fits this data. You can see that this is a little bit of an outlier, which means it doesn't really fit in like the rest of the points do. But as you can see, this line goes through and actually touches at least every single point. If we have purple, we're going to go to our quadratic regression. And as you can see, that doesn't really look like it would work, right? And it doesn't touch any of the points we want. Now we're going to do cubic regression in orange, and I'm going to zoom in here so you can see the line a little bit better. That one as well doesn't seem like it's a good fit, right? It doesn't touch more than just that one. It actually doesn't touch a single point if you look closer from our scatter plot. So we're going to say, okay, let's get rid of this quadratic and cubic regression. And we know we're probably going to have a line of best fit here, a linear regression. And here what's so great is I already mentioned, but it gives you the values in the bottom. So it says parameters, m is equal to this, b is equal to that. So all you have to do is just substitute those values in this equation. So calculate a linear regression model for the data and write the equation below. So we'd have y is equal to 21.85x plus 26.33, because again, I got those values directly from this m is equal to and b is equal to. Now, it asks us, okay, we'll calculate a quadratic regression for the model and write the equation below. If we go to our quadratic regression here, it tells you our values down here as well. So b and c is equal to 1, a is equal to 0. So we're going to have y is equal to 0, x squared plus x plus 1. So you could have actually also written y is equal to x plus 1 because we have a 0 here. So that kind of tells us y doesn't work, right? Clearly x plus 1 isn't our equation because this is our best line of fit. But like I said, this was our quadratic regression and obviously it didn't work out. But we got those values directly from here. B is equal to 1, C is equal to 1, A is equal to 0. Now let's do our cubic regression. So in orange, I'm going to get rid of that purple quadratic regression. And again, it gives us our values. So A is equal to 0 again, B, C, and D all equal 1. So we're going to plug that into our equation. And this you could also rewrite as y is equal to x to the second plus x plus 1. And obviously that's not a cubic, so that kind of also gives us another reason why that didn't work out, right? So it asks which regression appears to be the best fit. Well, we already discussed that, and it would be our linear regression. Moving on to the concept development, it says, okay, well, we have a profit in billions of dollars for the software company Electric Arts, Inc. from the year 1998 to the year 2004. And so t, where t is equal to 0, is the year 1998, because there's time since 1988. There's been 0 times, so that's the year of 1998. If you have t is equal to 1, well, that's 1 year after 1998. So that would be 1999. If it was 2 years after 1998, that would make it the year 2000. If it was 3 years after 1998, it would be the year 2001, and so on, okay? So then here it gives us the net revenue in billions of dollars. Your revenue is on your y-axis and your years are on your x-axis. So it says, okay, now create a scatter plot. So since these are such crazy decimals, we're just going to use Desmos to help us out. Again, you'd have to press the plus sign on the top left. You'd hit table. It would give you a table, and then you would plug in those values. So I've already done that for you. This is our scatter plot. I've also already inputted, I actually just kept these values, these regressions in here. When you have a table in here, it automatically goes by the scatter plot that's in your table. So here, I just kept my regressions here, and I'm just going to deal with them one at a time since they're color-coded. So, but if I have all 3 of these up at once, I see that the blue line, which is actually my linear regression again, right? My mx plus b, it's my degree 1 polynomial. So here I'm going to assume that the linear regression would be the line of best fit. Well, based on the scatter plot, linear regression. Then it says use your graphing calculator, in our case Desmos, to determine the regression function to model the revenue as a function of time. So it's asking us, okay, well, if you think linear regression is the best fit, you could have determined that without plotting these, because if you look at this line, if you were to put a line of best fit here, you'd probably most likely have a straight line. It doesn't look like it's going to be a parabola. It doesn't look like it's going to be a cubic, right, function. So we can assume that the line of best fit should be a straight line. So it should have been this linear regression. But again, here, they want our equation, so we're going to have to give them our equation. Again, it tells you your value. So m is equal to 0.122, b is equal to 1.04. So we're going to say y is equal to 0.122x plus 1.041. Again, I got those values straight from here. They give it to you because they create a line that's going to match that the most perfectly. Number 5 introduces us to the coefficient of determination. So the R value, right, R squared value, it's a measure that tells us how strong the relationship is between the two variables. So the closer it is to 1, the stronger the ability it for the independent variable to be a predictor for the dependent variable, the closer to 0 it is, the less strong that ability is. So it's asking, well, what is the regression? What is the R squared for your regression model? And if you actually go to your Desmos, they'll actually tell you what that R value and R squared value is. So here they're asking us for R squared, and we're going to give them 0.6974. So it asks us, what does that mean? Well, if we were to round this up, this 9 would round this to 6 up to a 7, so we'd have 0.7. This is closer to 1 than it is to 0. So that means it has a pretty strong ability for the independent variable to be a predictor of the dependent variable. Then it asks, okay, we'll use the regression model to answer the following questions. During what periods of time was the revenue of the software company increasing, and when was it decreasing? If we look closely at the scatter plot data, we can see that in 1998, from 1998 to 1999, it's increasing. 1999 to 2000, it's increasing. Then we get to 2002, and it's decreasing. Then you get to 2003, and it increased again. And then in 2004, it decreased back down again. So during what periods of time was the revenue increasing? Well, from 1998 to 2001, it was increasing. 2001 to 2002, it was decreasing. 2002 to 2003 was increasing. 2003 to 2004, it was decreasing. And then it asks, well, what happened in the year 2001 that could have caused that revenue to decrease? Well, there could be a couple things that might happen. So I'm going to let you come up with your own ideas, and we're going to share this in class and talk about it. Then it asks, okay, we'll use a model to estimate during what year would the profits surpass 4 billion. So we're going to go back to our line here, and we're going to say, okay, well, this is our line of best fit, so we're going to go by that because we have no other data other than the points that we plotted from our table. So looking at this line of best fit, they want us to know, okay, well, when will it surpass 4 billion, right? Well, we're looking at our timeline. We know our X values is the years after 1998, and we know our Y values is our revenue, right? So we are looking for 4 million. That's close enough. Try to get as close as you possibly can. But if that you can't, like I just couldn't right there, I'm going to say Y is equal to 4. So now I can at least pinpoint exactly where it's equal to 4. So here I have 24.218, comma 4. And here, this would be the years time after 1998 in years. So if we were to calculate what year this would be, it would be the year of 2022, and we would be at $4 billion in revenue. And keep in mind, we looked at 4 because way up here it says net revenues in billions of dollars. That's why I knew that I could go to 4 on the y-axis, not 4 billion, because that would be crazy. It'd be like 4 billion billions of dollars. Wow, that's a lot of money, right? So anyways, that's what it would be. This would be 4 billion. EA means Electronic Arts Inc. And this last question says, okay, well, if we check profits for EA during the year that we predicted, the revenue would reach 4 billion. And we can determine that it's not very accurate right away because we don't really have that much data. If we look back at our table here, we only have 6 data points. So that's not very accurate for determining long-term revenue. For all we know, they could go bankrupt and they could have no money by 8 years after 1998, or right now it's 2021. For all we know, they're already bankrupt, right? So we'd have to have more data to determine within that 24 and a half kind of years later after 1998, well, what profit would they have, right? We just need more data to make a more accurate assumption. And actually, the more data points that we have, the closer and more accurate our line of best fit will be as well. Okay? So we're going to do, you guys have an exit slip. Make sure that you're doing exactly how I modeled in the Desmos that I showed you. You're using Desmos, you're building your table, you're going to find your lines of best fit, you're going to have those lines, those linear, quadratic, and cubic regressions to figure out, okay, well, what would be my line of best fit here, what degree polynomial would fit this function the best, and then they also actually ask you for your R values in a couple of these questions too, but you can get that from your Desmos as well, okay? If you go on to the lesson 2, we're going to be doing a couple of these problems live. If you look, there's an entry ticket that we're going to do together live. And then there is actually another little problem. We're going to watch a small YouTube video. We're going to watch that together. And there's only 3 questions for us to answer. You guys can cross this part out. We're not going to do that part. And we're going to try to make the best line of fit for a roller coaster, which is going to be super fun. And that's it.